again, let me show again, where you should type in your questions. So, in your login window, you will see this questions window, which you can type in any of the questions you have. And then, like I said, I will take them at the end. As I mentioned, I should acknowledge the in-kind supports we receive from our different funding support partners. Without their support, we won't be able to conduct the work that we are doing. Agenda for today's webinar. I'm going to introduce why we use different metrics. What is the use of different metrics? And then go into levelized cost of electricity, which is the most common metric that we are using, have been around for a very long time, and then go through some of the limitations and misinterpretations of levelized costs, and then go through some 3 alternative metrics that have been developed in over the past few years, and then go through some of the observations and future research requirements. So why we need economic evaluation of alternative generation technologies? They are required, to inform, decisions, that pertains to electric power generation. They can be investment decisions, they can be regulatory decisions, or they can be, public policy related decisions. We ask questions like, what should we build to satisfy future electricity demand? That we would observe in the next 5 to 10 years, for example, or we would ask questions like what is the optimal level of renewables we would have in our electric power system. That could be one question that we may ask. And another question could be how can we capitalize on how can we use the advantages in the electric power sector can provide in terms of meeting our economic and environmental goals, for example. And then very quickly these decisions may go way beyond well beyond the electric power systems. So it's no longer a decision to invest or operate a power generating unit. We are asking other questions. How can we use the advantages or the value of electric power systems, to meet some of our other public goals, public objectives. And the complexities in an evaluation of electric power generation technologies involve a very high amount of economic and technical information, and because there's so much information, using a compact singular metric is useful, especially if there are a lot of decision makers are involved, who some may be electric power system experts, some may be not. So using a simple to easy to understand singular metric is useful, especially when there are different decision makers are involved. So the objective of this webinar is to introduce some of the ongoing developments in this space, in terms of using different developing different metrics, developing different assessment methods, assessment frameworks. But we do not advocate the use of any of the metrics that I'll be reviewing. That is not the intention of this webinar. The objective is to introduce some of these, and then to start a dialogue, because there's our decisions are becoming quite complex, and then there are recent developments that can help to digest the information that we have to go through. I should also note, in our March commodity report, commodity update, the electricity commodity update, we did publish an article on the same topic. You can access that article using the link that I have posted here. Now we'll then go through, the first metric, the metric that we have been using for a very long time, which is the levelized cost of electricity. And then, like I said, it is the most commonly used metric. So levelized cost of electricity of an electricity generation unit is its full life cycle cost per unit of electricity produced, or simply it is sort of the average cost of producing electricity using a given generating unit, given generating technology. It is, why it is so popular or visually appealing is it is using the levelized cost of electricity. It is possible to compare different generating technology, different generation units or generation units that utilize different technologies. Whether it is coal-fired generation or natural gas or any of the renewable technologies. And they may have unequal lifespans. Some may be good for about like 100 years, a hydropower plant, or some may be good for like a shorter time period, or could be operated for a shorter time period. And they do not, when we are comparing, they do not need to be the same capacity. And then they may have different cost structures. Some may require a higher amount of capital cost, and then some may require maybe moderate amount of capital but a lot of operational costs, fuel costs and whatnot. And then some of these costs may incur at different times. If there may be situations we just spend on capital, like in the case of like a renewable power generating unit, we spend a lot of capital and then virtually no operation costs or the fuel costs throughout the life. But if you look at something like a nuclear power plant, we spend a lot of capital at the beginning. At the same time, at the end of the life too, we have to spend quite a bit of investments to decommission the unit. And then we may also have long-term liabilities like how to manage the spent fuels, or how to manage how to manage the risk of CO2 underground CO2 storage in terms of a carbon capture and storage plant. And then the other thing is, we can also compare, units with different use profiles. By use profile, this is something that I'm going to keep, coming into describing throughout the presentation. Some units may have, complete flexibility to satisfy the electric power demand. Some may have some, constraints. So they have different use profiles, and then using the levelized cost, you can compare, the ones have different use profiles. So the estimation method, the simple explanation, definition of the levelized cost is, we divide the present value of all costs over lifetime of the plant in dollars. We divide that by the expected electricity generated over lifetime. And then these costs can be split into two main categories. Fixed costs that includes the capital and operating and maintenance costs, and then it could also include some decommissioning costs. And then variable costs is usually dominated by fuel costs, and then there may be some non fuel related variable operating costs. We also have like a denominator, like you see here, is the expected generation over lifetime. That means we have to assume some utilization or some electric power production for a given plant. And then we also have to take into account the financing aspect, how we're going to finance the plant. So this is the more complete definition or the calculation formula for the levelized cost, because it is the present value of that we have to consider. that we are considering in terms of the cost, we do have to, take a discount rate. We have to use a discount rate that pertains to the financing aspect that I mentioned. So the unit of the levelized cost is the dollars, is dollars per megawatt hour, or lifetime cost per unit electricity produced over the lifetime. And then here I am showing, just for the completion for your reference, I am showing, the levelized cost of electricity estimated for different generation technologies, that are to come online in 2025 in the United States. So I use the information presented in the annual energy outlook publication of the US EIA. Like I said, depending on there's a wide variation, quite wide variation of the levelized costs, across different generation technologies. I should also, point out, some technologies like, or like renewables that I'm showing here, their cost is dominated by the capital cost, as well as, the resource availability in different regions and so on. So how to interpret the levelized cost in, generating unit? It depends on, whose perspective, we have to look at. We have to, interpret this. So in the unit, like generating unit owner's perspective, levelized cost is the total revenue requirement per unit of electricity produced over its financial lifetime to achieve break-even, to achieve at least the break-even. In like a regulator's perspective, the public's perspective, or the electric power system's perspective, it represents, the long-term marginal cost of incremental unit of electricity, megawatt hour or the kilowatt hour of electricity added to the power system. Let's say our demand is increasing, we have to add, new power generation capability. So levelized costs represent the long-run marginal cost, include, both capital and operating, operating costs. And the main strength of the levelized cost is, it is based on net, like estimation is based on net present evaluation, net present economic evaluation, which is like a well understood economic assessment method. And the other thing is, as I mentioned before, it is the average cost. It is like, we have a lot of information: capital costs, operating costs, some financing assumptions, and operational profiles. All that information is compacted, or integrated into a single compact summary metric. And then the other advantage is, if you look at if you recall the estimation method, it is like a very, algebraic, simple, relatively simple estimation method. And then it is also, easier to interpret. But the limitations wise, levelized cost of electricity, LCOE, is estimated at the plant level. We would look at like a certain generating technology. We would, get information on, all its costs, like a life cycle cost, and we would divide that by, expected power generation. So it is done at, units, like, at the plant level or the generation systems level, but it is connected to this overall power system. That got, transmission line, like a, huge bulk transmission system. It got the end users, who demand electricity at different rates, different consumption patterns. And then it also has, other generating units. It could be like hydropower plant, a lot of, thermal units or other renewables. And then, when you are adding a new generating unit into the system, it would bring, some unique set of integration costs. It could be addition of a new, it might require the addition of a new transmission line, for example, or depending on what we are adding, this new generating unit that we are adding, it might require some additional, balancing services, that the grid will have to maintain. So those are, those types of indirect costs to the system is unique to the generation technology and the location of it, where we would site it. And LCOE does not measure those indirect costs to the system. So we do not get the full system picture. The other aspect is, like a levelized cost is a cost metric. And then if you look at the demand, demand for electricity is variable, and storage is costly. For storing electricity is costly. I should say it is still costly. It could change over time. Therefore, supply and demand must be matched across time and space. It's not just the time. Our generation may be at one location, and then our demand may be at various different locations. And then we may have, some transmission system constraints, or delivery system constraints. Considering all those things, they must be instantaneously matched. Therefore, the value or the price of electricity varies over time and location, due to the variability of the demand. And LCOE does not, take into account, that aspect, or the time varying, or the time and space varying nature of the value of electricity. So if we just compare the LCOE with the average price of electricity, it does not take into account that time, varying nature of the value of electricity, or that can be, obtained, or that can be capitalized by a given generating unit. So therefore, because it cannot, track the time varying nature of the value of electricity, LCOE or levelized cost may not measure the full economic value of a given generating unit. And then the other aspect is like a combination of the ones that I mentioned. Different generating units are differ by their dispatchability and the flexibility. If our demand is varying, it is valuable to have more flexible units. So you can change, you can then use the generating units to satisfy the time varying power demand. Not all generating units are equal in terms of those aspects. So I would argue, different generating technologies are not perfectly substitutable. So as a metric, levelized cost is poor for comparing technologies that have different operating profiles. So we use this metric to compare things, and but the metric cannot, it is poor in terms of comparing the ones with different operating profiles. So another way to way to look at this is, we can see this issue in another perspective. Electricity produced at we have two goods in here, right? So we have electricity produced by a unit, and then but we also have electricity that is perfectly matched the demand. We have, we produce electricity to satisfy the demand, and then we have this electricity that is perfectly matched with the demand, and then we need some additional costs in terms of transmission and grid balancing to perfectly match that power produced by a generating unit with the time varying demand. And then in order to do that, system will need additional costs. And then LCOE does not include those additional costs. And then, like I mentioned, LCOE does not. Does not measure the market value of fully measure the market value of electricity. And then these limitations becomes more pronounced with the higher amount of as we add a higher amount of intermittent generating units, or the ones when the system becomes in terms of generation system, when the system becomes quite heterogeneous, these issues become quite pronounced. Therefore, in terms of the full system cost, we only looked at the levelized costs, the unit specific costs, but we have other costs, other indirect costs in the system to perfectly match, that power produced by a unit with the demand. And then some of those costs include what we call the profile costs. The profile costs associated with some units can be perfectly dispatched. One way to explain that is some units can be perfectly dispatched, and then some can. And this is not just renewables versus thermal units. Some thermal units such as some coal units, and then some nuclear units, they have limited flexibility, right? So there are costs associated with the profile, and then because we have to match the demand perfectly with supply, there may be some balancing costs, because like I said, some units can ramp up and down quickly, or some units may have some some units have some unpredictability. Once again, in terms of like a variable renewables, or even some units may have some unexpected outages and so on. So there may be some but demand still need to be satisfied, so there may be some balancing costs. And then the bulk grid cost pertains to anything to do with like a transmission, like addition of a certain generating unit may require new transmission addition, or there may be some operational changes that we have to make to deal with the congestion involved with the transmission system. So that all those include in what we call the bulk grid cost. So the full system cost includes the generation cost, as well as those indirect costs that are incurred within the system, that incur for the system, in terms of matching that power produced by a unit with time varying demand. And the full system cost, to get a full picture, we need to incorporate all those additional costs, and LCOE does not incorporate all of them. And therefore, there are some alternative metrics that are being developed, by different organizations. So, one of the one metric, that I want to go over is what we call the levelized avoided cost of electricity, or LACE, rather. This metric is developed by it was developed by the US EIA. It measures a given power generating unit's value to the grid. How it measures the value. It estimates what we call the avoided cost. For a new generating unit, LACE is defined as the cost of providing energy and capacity to the grid that would be avoided if this new generating unit to be built and operated. So it is an avoided cost due to the addition of this new generating unit. And then within the LACE framework, it is interpreted as the revenue available to the new generating unit. But for all intents and purposes, we can interpret that as this is the cost that can be avoided by the addition of a new generating unit. Therefore, it can be considered as the value of a value metric of the new generating unit. It is estimated as, LCE is estimated by, dividing the present value of energy and capacity revenue that can be obtained for a new generating unit in a given power system. We have to, this is a system metric. It depends on the system we are looking at. So in a given system, for a given generating unit, we divide the present value of energy and capacity revenue by the expected power generation throughout the life of the generating unit. So the energy revenue is calculated. The latest calculation by EIA, they split say a given year into different time slices, and then the energy revenue is calculated by forecasted electricity price at a given time period by power produced by annual megawatt hour of electricity produced by that generating unit in that time period. So that is how the energy revenue is calculated, and then the capacity revenue is calculated by capacity payment times what we call the capacity credit. What is the capacity credit of a given unit? How much we can rely on a given generating unit to satisfy the time varying electricity demand. So that is how the capacity payment is calculated, and in all are brought to the present value using a discount rate, and then divided by the expected power generation. And then like I said, it definitely expired. Now we go into the systems level. So we require, so latest estimation requires any information about how the system would operate without the new generating unit. So I should say it is a complementary metric. So we now calculate the value. What would be the value of the power generating unit? So the more important insight. So it is a complementary metric to the LCOE. So it is the more important comparison is how does it compare with the levelized cost? So we can argue if the LACE is a value metric and then levelized cost is the cost metric. If the value is more than the cost, or LACE is more than LCOE or levelized cost, then a given power generating unit is more competitive or have a higher value, so or more desirable. To provide some, like some, to show you some illustrative results, I took. So US EIA now calculate, in their annual energy outlook for all generating technologies and all regions across the United States. There are kind of like 9 of them. In all those regions, they calculate both levelized costs in the x-axis, in the horizontal axis, and the levelized avoided costs or LACE. So whenever LACE is higher than or at least equal to the levelized cost, then the unit is more desired. So here, but it is a system metric. So the value that can be obtained by a generating unit changes over time. So here they are kind of like more lighter dots show the comparison for 2025, and then the darker ones for 2040. As you can see, if you look at like natural gas combined cycle, in many regions it is at least as much as the levelized cost. So it has sufficient value to be break even. And the same for solar PV, across many United regions in the United States, both now and 2040 in the future. solar PV seems to have, a higher value or at least equal value as the cost. Therefore, they can be considered as, competitive or desired generating technologies in those respective regions. So the other metric that I want to go through is in what we call the value adjusted. So I should mention, so the LACE is a value metric that would complement, LCOE. And then the other one is, VALCOE, or the value adjusted LCOE, or levelized cost, developed by the International Energy Agency. And then it enables the comparison of different power generating technologies by considering both their cost and then value. So the VALCOE or VALCOE estimation starts with the LCOE, or the levelized cost, and then adjustments are made for energy value. So you start with the levelized cost, and then you make adjustments for energy, and then capacity and flexibility of that particular generating system, compared to, for example, if this is, say, the energy value of the unit. So energy value is defined as, depending, what is the value or the value of power produced by energy produced by a unit, given by considering the time varying, value of price, or time varying price or the value of electricity in a given system. So you estimate the value for energy value, for example, for a given unit, and then we look at, what is the system average energy value? What is the average value of energy of the system, or this E bar is the system average value of energy. And then if the unit has a higher value, compared to the system average, that this part becomes, negative. Then and then you make those adjustments for both energy, capacity, and flexibility. So basically, you estimate the those energy, capacity, and flexibility value for a given generating unit, and then compare that with the system average, and then the difference is what we call the value adjustment, and then it is added to the LCOE. So here, as I am showing here, you start with the levelized cost, and then let's say it has a lower energy credit. So that means if it has like a higher energy value, that means it has the adjustments is negative. So you lower the overall cost, and then it may have a lower capacity value than the system average. So you then add the adjustment would be positive, and it may have a lower flexibility than the system average. So therefore, that also added. So we make those energy, capacity, and flexibility adjustments to come up with a metric called the value adjusted levelized cost, and then that represent the cost of production, like unit specific cost, and then the value it would bring into the system compared to the average. So basically, if so it adds extra value or to a generating unit if it provides more of the three services. Right? To illustrate, the most recent World Energy Outlook report from the IEA, International Energy Agency, actually calculated levelized VALCOE for the value adjusted cost of electricity, levelized cost of electricity for different regions. I am showing the results for the United States and European Union for different generating units. So lower the value adjusted cost, the more competitive the power generating units. So I should show. So one would think, okay, this is if any unit that has like a lower flexibility, such as like a renewable, would have like a low, like a lower value, or would become less competitive. But that wasn't the case, right? It is a combination of declining costs, measured by levelized cost, as well as how does their flexibility or the capacity credit varies by compares with the system average, and that system average also changes over time. So when the system becomes overall more flexible, the penalty a renewable unit would see would be different, or would go down, as we can show here. So solar PV, for example, would see, will see like a, become quite competitive in the United States. This yellow line. Or the other thing is solar PV with storage, especially in the European Union. So solar PV with storage will be even more competitive compared to many other generating technologies because of the additional flexibility it would bring into the system. And the energy value it can capture from the system. So the last metric that I want to go through is what we call the system levelized cost of electricity. It is developed by Leon Hurt and Farco Ukert at the Potsdam Institute for Climate Impact Research. So what they did was, they define the system LCOE as the addition of LCOE or the levelized cost of electricity, and those integration costs that I talked about, I mentioned before. So it is defined as a summation of the two, and then they also split profile, the profile cost into three other categories, what we call the overproduction cost. For example, at higher penetration levels, of variable renewables, for example, there may be overproduction. There may be production more than the demand. Therefore, some spillage would occur that will increase the overall cost of the variable unit. So that would be the overproduction cost, for example. And then they also add like two other components. They call them full load hour reduction. This would be the impact of the other units in the system. For example, if you have a high, like a flexible unit, or like a variable unit with very low marginal cost, that will take away the operating hours, the full load operating hours of other flexible units in the system, or dispatchable units in the system. That will increase the overall cost to the system. So that is called the full load hour reduction. And then also the backup cost is, due to the any forecast errors of variable renewables. So what they did was, the main contribution that they made, the authors made in development of the metric is, like we've been doing this. I mean, this type of research, estimations have been, like different groups, different parties have been developing this type of metrics for a very long time. The contribution they made was, but depending on, who estimate, who does the system, who made the assessment, who developed the assessment method to estimate the system cost. People use different metrics, different ways of quantifying that. The main contribution they made was, they provide like a very like a repeatable mathematical definition. Like they basically add some clarity into how to estimate the profile cost in a given system, and the balancing cost, and the grid cost, the transmission addition cost. And then provide like a repeatable mathematical framework that can be repeated to to different systems. And then in their like a seminal work, they also publish like a simple way of estimating the profile cost, but that the mathematical definition that they provide is actually one do not have to does not have to use the same profile cost estimation method to use the to calculate the system LCOE. To provide some results, one here I am showing the system LCOE. The authors calculated for Germany. So this is the system LCOE for wind power in Germany at different penetration levels. So it goes from 0% to say something like a 40%. And then what the main observation is, profile costs. The ones that associated with the variable nature of the generating unit is the highest contributor for the system LCOE, system levelized cost, and then it also increases, like a system levelized cost increases with the penetration level. As you increase the amount of wind in Germany's power system, it requires more and more balancing costs, and then more and more overproduction costs. Therefore, with higher integration, higher penetration, the system LCOE increases at around something like a 20%. Around like a 20% penetration level. They estimated the system LCOE, the profile cost, like integration cost component, which is a sum of a profile and then balancing cost and the grid cost, is same as is comparable to the LCOE. So I mean, we can go through some of the details during the Q&A period. To summarize, the main thing I want to mention is, levelized cost is incomplete metric for comparing different generation technologies, especially when they have different operating profiles. And then it also lacks representation. It is a cost metric. It lacks the representation of the value of a generating unit. And then it also excludes the indirect costs that would incur within the system. And then metric, other like a new metrics such as LACE, VALCOE, value adjusted cost, and then system LCOE actually provide complement complementary information. More provide like a more complete picture. But the main thing is those are system metrics. They are there estimated at systems level. Therefore, in order to estimate those things, we require we need more systems level analysis method or simulation tools, and that can be computationally expensive. However, they provide a complete picture. For example, the metric like system LCOE can suggest what is the optimal penetration level of variable renewables in a given power system. And LACE and VALCOE can provide a complete information about the competitiveness of a certain generating unit, again in a given power system at a given point in time. And the other thing I want to mention is it may appear as if the alternative metrics that I mentioned paints like a pessimistic picture for especially for the variable renewables that see huge reduction in cost over the last few decades. But I would argue that's not the intention. That is, although it may appear like that one, the use of these alternative metrics allows identification of and evaluation of integration options that would actually alleviate avoid the economic barriers for the development of high share of variable renewables. For example, it is a system metric. If you recall the electric power system, you have the demand side, you have the supply side, you have the transmission. You also have, other like a storage systems and so on. So if we use like a system metric, we can actually take into account, the how we can lower the overall integration cost using other metrics such as inclusion of storage or sector coupling, or the demand side management, for example. So all other like a systems level tools that we can use to lower the integration cost can be estimated or evaluated using systems level metrics. So as like a future research requirements, like I said, these require a lot of like systems level analysis methods or model developments and the data set developments, which is not easy. I mean, at CERI, for example, we've been trying to do this in a systematic manner for a very long time, and then I know that is true for other parts of the country too. I mean, we especially lacks like a transparent and long run models available, like systems level models available across Canada. I know there are efforts at Natural Resources Canada and then different academic communities to mitigate that. So what I want to argue is this is as a final point, what I want to mention is these different metrics can provides us more like a more complete information, but estimation in a robust manner needs more work, and which requires like a higher level of collaboration among different groups, and which is at this point I would argue a research requirement, like an area that we need further research in this space. I should, this presentation, for this presentation, I use these posted references. I benefited from these references, and then all these references are available in the public domain. So if you require more information about any of these metrics, I strongly suggest you go through them. And like I said, I have given almost all are publicly available documents. So thank you very much for your time. Let me take some questions that you have right now. Looks like I have a lot of questions. So so one question is Lars Remberg says, my understanding was that LCOE is average cost metric, not marginal, since it is average total cost over total production by the generating unit. Is that a fair statement? Yes. In the short run, yes, it is. It is an average metric, not not a marginal metric in the short run. Our good colleague Leonard has a question about VALCOE. Is the VALCOE have is the VALCOE results being presented that include environmental and carbon value? My understanding is carbon cost is included. But other environmental concerns such as sulfur mitigation costs and then so on. Again, as long as they are part of the overall operational costs, they are included. So another question from Leonard. Since solar and wind have complementary generation profiles, can you calculate system LCOE based on penetration of both? Yes, you can. Is that again? I guess this is the main strength of system metrics. So if I interpret the question correctly, so you have two generating systems, two types of generating systems. two types of variable generating systems: so wind, which has its own production profile, and then solar energy, which has its own production profile. And then in some regions, for example, in Alberta, they are quite complementary. So would that be captured in the system LCOE estimation method? It is, because it does take into account what is the overall capability to follow the to satisfy the time varying demand, and the overall framework does include that one. Thank you for the question. Let me see whether I have other questions. So looks like those are the questions that I have received so far. I know some of the attendees actually logged out, but those who still with us, do you have any other questions that you or require clarifications of any of the things that I that I talked about? I should also point out we do have a few other online events, webinars and workshops that are being organized by CERI in the coming weeks. A webinar on one of our upcoming projects, studies on value-added use of oil and natural gas, is scheduled for June 29. Would be quite valuable, interesting presentation. Do you have any other questions? So I should emphasize again, especially system LCOE metric. I did not go into any of the calculation methods, simply because the mathematical framework of estimating the profile cost and the balancing cost does have a lot of math involved. So this wasn't the place to go through all of them. I would strongly suggest those who are interested, if anyone's interested, go through this seminal paper by VALCOE and Leon Hurt. I have provided a link for the although the published version is requires subscription. And the link that I have provided here is available available free, through the author's website. I should also point out you will get a copy of the presentation, but this particular figure from IEA, it may not be included in the presentation simply because of like a copyright issue. So you would not get this figure. So everything else you would receive. So looks like that's all the questions we have. Thank you for your attention. Thank you for attending this webinar. I hope the information I provided was useful for you, interesting for you. This was a little bit of a different webinar because usually we run webinars on studies that we develop, we conduct. But this is a topic that we thought this is a topic that may be of some contemporary importance, because like I said, questions, we expect the electric power system to provide a lot of services, to as the means of achieving a lot of objectives, environmental and economic and energy objectives. And then we thought starting a dialogue, starting a conversation on how these different how different metrics can be developed, how the importance of developing new evaluation methods. So I hope this was useful for you. If you have any questions, please feel free to approach us through our info. My apologies. So info@ceri.ca email. I'm happy to take your questions. You can send questions through info@ceri.ca email or by direct email. Thank you for your time. I'm gonna end the